At first glance, a cucumber doesn't seem like the kind of object that requires engineering precision. It's soft, it's fragile, it's common. But hidden beneath its green skin lies a logistical paradox, one that quietly moves over 4 million tons of this fruit across oceans every year. Not in bulk like grains, not with the rugged resistance of root vegetables, but inside high-precision containers where a 1-degree deviation can compromise the entire load. Because cucumbers don't travel, they respond to temperature, to pressure, to gas concentration. They behave quite literally like living hydraulic systems. And that changes everything. Inside a refrigerated shipping container, packed with cucumbers, nothing is static. The fruit continues to breathe, releasing moisture and ethylene, a natural plant hormone that accelerates ripening and decay. If that gas isn't constantly expelled and balanced, the container becomes a sealed chamber of self-destruction. The internal climate must be managed with the same delicacy applied to a submarine's pressurization system. This is where the comparison begins. Just as a submarine adjusts its ballast to control depth and internal pressure while submerged for weeks, these containers must maintain a stable internal atmosphere across thousands of kilometers, where even minor thermal shifts can cause condensation, tissue breakdown, and irreversible loss. It's not cooling, it's environmental orchestration. And the orchestration is not about brute force. It's not about dropping the temperature to its lowest setting and hoping for the best. Cucumber logistics require something far more intricate. Unlike harder fruits, cucumbers demand precision over power. Their ideal transit temperature is narrow, usually between 10 and 12 degrees. Below that, internal chilling injuries form, degrading the texture before they even reach customs. Above that, microbial activity accelerates. The difference between a successful shipment and a rejected load often lies in the microclimate within a single pallet. And this precision doesn't come from refrigeration alone. It comes from sensors, sealed environments, and real-time atmospheric correction. That's why the containers used for long-distance cucumber transport are far closer to marine vessels than most would ever imagine. Like a ship beneath the surface, each container becomes an autonomous environmental system, managing pressure, temperature, airflow, humidity, and gas exchange with military-like calibration. On screen, we see a simulated cutaway, the container's internal environment illustrated next to a submarine's pressure chamber, pressure equalization curves, ethylene removal cycles, CO2 balancing valves. Each graph mirrors the other, each system responding to invisible forces in motion, and each cucumber inside, holding 96% water, behaving more like a biological sensor than a static object. This is the part of agriculture we rarely see. Not the harvest, not the market, but the invisible space in between, where machines don't till soil but balance ecosystems in motion, where precision farming meets precision logistics, and where something as humble as a cucumber becomes the center of a quiet, daily feat of engineering. The journey is long, the technology exacting, and what keeps it all working is not force, but synchronization. In the world of fresh produce logistics, the most critical decisions are often made long before a shipment reaches a port. For cucumbers, the defining moment isn't the ocean voyage, it's the first hour after harvest. The phase known as pre-cooling is where everything begins, or breaks. If that step fails, no sensor, no refrigeration system, no ventilation redesign will save the cargo. Because cucumbers, with their 96% water content, store heat not like a vegetable, but like a liquid reservoir. And unlike other crops, the damage caused by heat retention isn't always visible until it's too late. The fundamental issue lies in how cucumbers respond to latent heat. Once harvested, the fruit begins to release internal moisture, triggering physiological stress that accelerates degradation. Yet, in many post-harvest centers, cucumbers are treated with the same cooling protocols used for leafy greens or tomatoes, protocols that prioritize speed over compatibility. A rapid temperature drop might seem ideal, but for specific cucumber cultivars, cooling below 10 degrees activates chilling injuries at the cellular level. Microscopic fractures form inside the tissue. Texture changes. Shelf life drops. The damage becomes irreversible. All of it caused not by pathogens, but by a mismatch between biology and process. This is more than theory. In 2021, a cooperative greenhouse in southern Spain experienced this firsthand. One morning, a batch of greenhouse cucumbers was harvested in full sun, but cooling operations were delayed due to a mechanical fault in the hydrovac system. The cucumbers sat in ambient air for just under 2 hours before pre-cooling began. The temperature of the pulp reached an 18.5 degrees nags, well above the safe range. Days later, by the time the shipment arrived in Rotterdam, 17% of the load was lost. Texture collapse, internal browning, market rejection. The audit didn't blame shipping or customs or containers. It traced the loss to that 2-hour window in the packing facility. This makes one thing clear: cooling cucumbers isn't about temperature. It's about timing, rhythm, and equilibrium. Too fast, and the tissues harden unnaturally. Too slow, and internal steam builds. It's like stabilizing a diesel engine at idle. If you accelerate too quickly, the system stalls. If you idle too long, it overheats. The same logic applies to post-harvest cooling. The airflow must be steady. The thermal load must decrease gradually. The water inside the cucumber must have time to reach equilibrium with its environment, without triggering internal stress responses. From the outside, it's just a box of vegetables, but from the inside, it's a battle of thermal inertia, water physics, and metabolic timing. And this moment, this invisible cooling choreography, is what determines whether a cucumber makes it across a continent or gets rejected before it ever leaves the dock. Before we move on, take a moment to check the pinned comment below. If you're fascinated by how precision shapes the world of fresh produce, there's something there you won't want to miss. It's made for those who see logistics not as routine, but as engineering in motion. When we imagine a refrigerated container, we often think of temperature as the central factor. The cold air flowing in, the perishable goods protected, the system working like a high-tech cooler on a massive scale. But inside a reefer unit, transporting cucumbers across oceans, temperature is only part of the equation. What truly preserves the quality of the cargo isn't just how cold the container gets, but how the air moves within it. The science of airflow, often hidden beneath the surface of logistics discussions, quietly defines the success or failure of thousands of tons of fresh produce. Cucumbers are especially sensitive to airflow design because of how uneven temperature distribution affects their structure. Laminar airflow, smooth, continuous, and directionally guided, is critical. It ensures that every part of the container, from the front pallets near the fan to the rear corners near the exit vents, receives consistent cooling. But in many conventional containers, airflow behaves more like a turbulent system. Microcurrents swirl unpredictably between crates, creating hot and cold pockets that the sensors don't always detect. In a 12-meter container, a variation of just 3 or 4 degrees Celsius from one end to the other is enough to trigger localized dehydration, mold formation, or cellular collapse. This variation might seem small on paper, but when applied to a perishable product with a water content of over 90%, the consequences multiply quickly. During a 2022 export run between the port of Santos in Brazil and Hamburg, Germany, an experimental adjustment was made to the duct curvature inside cucumber containers. The change? A redirection of airflow using slightly angled vanes to reduce turbulence around the container edges. The result was a measurable 11% reduction in dehydration losses. That figure didn't come from software projections. It came from pallet weight differentials upon arrival, monitored, recorded, and confirmed across dozens of units. In another instance, a major Chilean exporter began to notice strange inconsistencies in product quality within identical containers. Some pallets near the rear doors arrived with wrinkled skins and internal softening, while others remained pristine. Instead of replacing cooling systems, they commissioned a series of infrared scans across their shipping containers. The images revealed clear hotspots near the upper corners, areas where airflow had failed to reach. The solution was not more refrigeration, it was better direction. Ventilation shafts were repositioned, flow paths were recalibrated. In the following season, the rejection rate dropped dramatically. In financial terms, the improvement was worth nearly $240,000 in retained cargo value. The truth is simple, but rarely acknowledged. A cucumber container isn't just a cold box, it's a dynamic airflow chamber, closer in function to a mining ventilation shaft than a warehouse refrigerator. Air must be engineered to move with precision, not just to reach the product, but to wrap around it, flow through it, and exit without recirculating excess moisture or heat. What protects the fruit isn't temperature alone, it's the direction, velocity, and harmony of the environment it travels in. In this invisible choreography of wind and cold, the duct becomes the conductor, and the cucumbers, row after row, rely on its performance to survive the voyage. The global journey of a cucumber is more than a matter of logistics. It is a performance of engineering precision, biological understanding, and technological choreography that must unfold with absolute consistency across thousands of kilometers, over land and sea, and through shifting climates. Each cucumber that arrives crisp and intact at a supermarket in another continent is not the product of luck. It is the outcome of a chain of decisions made by engineers, agronomists, logistics coordinators, and machinery systems, all working in synchronization to maintain life in transit. This isn't about moving produce. It's about preserving function within living systems during transport. At this scale, agriculture stops looking like farming and starts resembling applied mechanics. Inside each refrigerated container, systems operate not independently, but interdependently. Ventilation ducts don't just push air. They must match airflow velocity to cooling rates, allowing moisture to be absorbed at the right pace. Temperature isn't merely reduced. It is managed through a feedback loop that anticipates ethylene buildup and adjusts accordingly. CO2 levels are not incidental. They are controlled with automated gas exchange cycles, ensuring the internal atmosphere supports metabolic stability rather than accelerating senescence. Every load becomes a mobile biome, where physiological processes are maintained not through chance, but through machine-aided design. This complexity brings to mind another machine that depends on synchronization for its function: the combine harvester, a marvel of agricultural engineering. The harvester must keep every component, from blades and conveyors to sensors and storage augers, moving in perfect timing. If one element is out of sync, grain is lost, parts are damaged, and the operation halts. The same principle governs cucumber logistics. From the field to the cooling chamber, from the container to the distribution center, each process must perform in harmony with the next. There is no tolerance for improvisation. Everything operates under tight margins and tight schedules. In this context, innovation isn't just about introducing new technologies. It's about orchestrating existing systems with intelligence. One of the clearest examples is the Dutch Flower Group's use of dynamic reefer calibration. By embedding microsensors inside cucumber shipments and continuously adjusting the cooling cycles and airflow in response to real-time data, they achieved a 14% reduction in energy consumption without increasing product loss. This wasn't an energy-saving gimmick. It was mechanical responsiveness applied to biological variability. The container became a living chamber, responding, adjusting, preserving. And that changes how we see these operations. When we stop thinking of cucumbers as fragile goods and start seeing them as complex systems in transit, systems that breathe, respond, and degrade in response to mechanical variables, we begin to understand the true nature of agricultural logistics. It's not just supply and demand. It's not just fields and freight. It is a form of invisible engineering, running quietly beneath global trade. Imagine overlaying two timelines. On one, the internal degradation of a cucumber across 7 days in transit, softening, dehydration, pigment loss. On the other, sensor data showing fluctuations in airflow velocity, thermal inertia, and vibration. Where the curves flatten, where the variables stabilize, is where the cargo succeeds. These charts, rarely seen outside control rooms and post-harvest audits, represent the hidden performance of the global food system. They are proof that modern agriculture isn't only grown in the soil, it's also built, calibrated, and steered by machines. In this convergence of engineering and biology, what appears simple becomes remarkable. And the cucumber, one of the most delicate fruits in global trade, becomes a symbol of something much larger: the silent, synchronized intelligence that feeds the world. Before you go, take a second to check the pinned comment. It's not part of the video, but it might surprise you in the best way.